The next topic is Plumber's view of chromatography. Here, let's look at this figure. This is what you actually get when you run the chromatograph. Okay, gas chromatograph or liquid chromatograph. Yeah, the whatever. Yeah, which chromatograph you run, you will get this type of chromatograms. Okay. So the x-axis is time, okay, and y-axis is detector response. Yeah, various detectors are used. Okay, you'll see soon. And here you inject your sample, right, your mixture sample, in the column, and since the column has a length, okay, your samples, your analytes, several analytes in your sample now moving through the column, and then depending on how strongly they interact with a stationary phase, in the time their time to come out of the column are different. Okay, in this case here, uh, the methane, you mixed methane, octane, and some unknown gas and nonane. Okay, and when you inject here, in this case the methane comes first, okay? Because this methane has virtually no interaction with the stationary phase, so it comes first, but it takes time. The time is defined here T sub m. Okay, because the methane should travel along with the mobile phase, and it takes time. But here, although it takes time, so don't think that methane has some interaction with the stationary phase. But actually, let's assume simply the methane is not retained uh, in the column. Okay, this is the time is defined as Tm. Yeah, Tm is unretained mobile phase travels through column in minimum time. Okay, but octane and unknown and nonane, the retention time, T is the retention, Tr is the retention time. They are all different, okay, depending on the interaction with the stationary phase. Okay, so the volume flow rate is the volume of a solvent per unit time through column. Okay, it is expressed in terms of, for example, 0.30 milliliters per minute. Okay, time usually is a minute, not second. Okay, second is too short time. And linear flow rate, as this one name indicates, it is the distance per unit time. For example, 5.3 centimeters per minute. Okay, from here we can define several terms. So here the adjusted retention time Tr prime is Tr minus Tm. Okay, in this figure, although this unknown, this retention time is Tr, but actually the Tm is in the every peak contains Tm. Tm is just because of the length of the column, right? So this is not a true retention time. So you have to subtract this Tm out from the Tr. Okay, so Tr prime, this one from here to there, that is the adjusted retention time. Okay, and here's the capacity factor, or it is also called retention factor, is defined as this one. Okay, the symbol is K. K equals this one, Tr adjusted retention time divided by Tm. Okay, Tm. So which indicates that if K is larger, that means the larger retention time. Okay, that means we say the capacity factor is larger. Okay, then relative retention is defined by this alpha, the symbol alpha, and alpha equals, the ratio of adjusted retention times. For example, here this one is TR2, okay, and let's say this is TR1, yeah, is always greater than 1, or if TR1 is TM, okay, yeah. Okay, so far it's very easy now and easy to understand. Yeah, here's the example. Yeah, retention parameters. Okay, let's read the question. A mixture of benzene, toluene, and methane was injected into a gas chromatograph. Methane gave a sharp peak spike, okay, in 42 seconds, whereas benzene requires 251 seconds, and toluene was eluted in 333 seconds. Find the adjusted retention time and retention factor for each solute, the relative retention and unadjusted relative retention. Okay, yeah. Uh, if you know the definition of each term, and it is easy to calculate. Okay, so adjusted retention time for benzene is what? 251 minus 42, which is for the methane. Okay, and you get 209 seconds. By the same way, toluene, for toluene, the adjusted retention time is 291 seconds. Okay, and what are retention factors? Okay, for benzene K, it is defined by this one, and then TR in this case is not the adjusted retention um, time. And simple, this is the apparent retention time. Okay, so 251 minus 42, and divided by 42, and you get 5.0. Okay, and by the same method you get the K value for toluene uh, is which is 6.9. Okay, and relative retention is expressed as a number of greater than unity. Okay, R must be greater than unity. Okay, so for the two solute, which is benzene and toluene. Okay, so toluene Tr prime, yeah, must be in a numerator, and Tr for benzene must be in a denominator. Okay, and then you get 1.39. Okay, but if you use unadjusted retention, relative retention, let's say that there is gamma, and for toluene is 333, and Tr for benzene is 251, and then you get 1.33. Okay, you notice alpha and gamma values are different. Okay, although small. Okay, so test yourself. Ethyl benzene was eluted at 350 seconds. Find its retention factor and relative retention and unadjusted relative retention for ethyl benzene and toluene. Okay, in this case, ethyl benzene is retention time is greater than the toluene. Okay, for to with respect to toluene, the relative retention, unadjusted relative retention is here 1.051. Okay, yeah, you may check it. Okay, and let's consider the relation between retention time and partition coefficient. Okay, and in a previous lecture, we learned the partition coefficient. Okay, if you are confused, you go back and take a look. Okay, the K is what? Here we retention factor we defined here, retention factor or capacity factor. Okay, and we define that way, and also we can calculate the K value equals time solute spent in a stationary phase divided by time solute spent in mobile phase. Okay, so if uh, you know, the time solute spent in mobile phase is at this is the smallest time, okay. And for the if these times are the same, that means that the no retention, no? For example, for the methane, okay. um, anyway, you carefully read, you know, this one time solute spent in in stationary phase. So that means what? Solute now interacts with the stationary phase, so that makes the time you know, bigger than the time spent times solute spent in the mobile phase. Okay, here is an example. If the solute spends all its time in the mobile phase and none in the stationary phase, that means what? The solute doesn't have any interaction with the stationary phase. Okay, it would be eluted in time tm. Okay, in the case time, you know, time in numerator and time in denominator would be the same. Okay, just like you know, the methane case here, methane. Okay, in the case tr equals tm and k factor uh, is uh, 0. Okay, because the solute spends no time in the stationary phase. Okay, no time, it doesn't have any interaction. All right, tr equals tm and yk equals 0. Here you use this equation. Okay, tr equals tm and so k equals 0. Okay? But suppose that solute spend equal time in the stationary and the mobile phase. Okay, not this one, numerator and denominator would be the same, or tr is all the time, tm is always there. Okay, that means the tr is twice that of uh, twice tm. Okay, um, so tr equals 2 times of tm, so k, you know, the capacity factor equals 1. Okay, using this equation, when a solute spends 3 times as much time uh, in the stationary phase as in the mobile phase. Okay, and uh, tr equals tm is always there, and plus 3 times, it says spends 3 times plus 3 tm equals 4 tm. Okay, in this case tr equals 4 tm, so k value is 3. Okay, using this equation. Okay, from these considerations we can write this equation here. See, here k, this is this definition is a k. Actually this k, this one equals, this ratio equals moles of solute in stationary phase divided by moles of solute in mobile phase. Okay, you understand? For example, if solutes spend equal time in stationary phase here, that means the moles of solute in stationary phase, yeah, is uh, what? The same, uh, no, with twice of the moles of solute in mobile phase. Okay, yeah, this equation holds, and k can be expressed as cs multiplied by vs divided by cm multiplied by vm. cs is solute concentration, vs is what? Here, let's see, volume flow rate for solute here. Yeah, cm is for the you know, the no retained species. Okay, it is you know, this equation is expressed by this equation. Okay, yeah, here, you know, I wrote here definition. Yeah, so cs is a concentration of solute in a stationary phase, vs is a solute volume of the stationary phase, and Cm is concentration of solute in the mobile phase. Yeah, M is mobile, Vm volume of the mobile phase. Okay, yeah. Okay, so here concentration multiplied by the volume gives the moles. Okay, by definition. If the column is run slowly enough to be at equilibrium, the quotient Cs over Cm is the partition coefficient K. Okay, let's consider the situation that the you move the mobile phase slowly, and then at every moment there will be an equilibrium of solute um, in stationary phase and mobile phase. Okay, and this ratio is constant, and it is the same as partition coefficient. Okay, now you have to think in that way, in a way that um, the solute, okay, solute now is partitioned between stationary and mobile phase. Okay, and then under the equilibrium condition, this ratio is the same as partition coefficient K. All right, so here capacity factor or retention factor can be rewritten here. You see, this ratio is large K, which is the partition coefficient, multiplied by Vs and divided by Vm. Okay, and using equation 17, and it is given by this one. Okay, yeah, this is the capacity factor. Okay, you understand? The original definition of K is given by this one. Okay, and the numerator is Tr prime, adjusted retention time, divided by this one, Tm. And alpha, here T adjusted retention time proportional to capacity factor. Okay, here this is proportional to capacity factor, and also this is proportional to what? Partition coefficient K. Yeah? So here we can write the relative retention alpha. Yeah, alpha. This is original definition. The ratio of adjusted retention times, and also alpha equals the ratio of capacity factors. Okay, K2 over K1, and also this is the same as partition coefficient ratios. Okay, large K2 over large K1. Okay. The relative retention of two solutes is proportional to the ratio of their partition coefficient. Okay, this relation is the physical basis of chromatography. Okay, yeah, you understand now, right? In a solvent extraction, okay, the at the beginning of this chapter, we first considered the solute now distributed between two solvent. Okay, yeah, yeah, and we defined the partition coefficient. Okay, and likewise in chromatography, the solute is distributed between stationary phase and mobile phase. Okay, yeah, the the things are equivalent. But in this case, but usually if you flow the mobile phase very quickly, and there may be not a equilibrium, but let's assume that the equilibrium, every time equilibrium be reached, then this ratio equals partition coefficient. Okay, yeah, that's the physical basis of chromatography. So for the solutes, different solutes, solute A, B, and C, yeah, like that, and they all have different partition coefficient. Okay, that's why, that's how we can separate each component. Okay, through the along when the solutes moving along the chromatographic column. Okay. Yeah, let's stop temporarily here.